introduce David, was it Bacher?
Bacher.
Who's working on his PhD at the University of Southern California in Los Angeles. His research focuses on guidance, navigation, and control for on-orbit assembly, servicing tasks. He holds an MS in Astronautical Engineering from USC and a BS in Mechanical Engineering from Georgia Fox University.
Thank you for the introduction. I'll go ahead and jump right in to my presentation on LQR attitude control design for an on-orbit assembly spacecraft. Jumping in with a little bit of the motivation for this work. On-orbit assembly of large space structures is a field that's getting a lot of attention recently because space missions are fundamentally limited by the mass and volume constraints of the available launch vehicles. And we're starting to see with missions like JWST that we're getting to the limit of what we can reasonably fold up and put into a rocket fairing. Even with some of the really large launch vehicles that are coming out like Starship, we're still, the space industry keeps proposing missions that are even bigger. So this is an example of some of the space telescope concepts that have come out over the past 20 or so years. I want to highlight the one on the right. This is a concept that's being worked on at my lab at USC called Optical Reef. The concept is that you have an in-space assembled telescope that can be functional as it's being assembled. So it starts out as a 10-meter telescope. It can go to a 20-meter, 30-meter, up to, I guess we'll find out what the limit is as we're developing this concept. But we're proposing upwards of 1 kilometer, and the main reason why is because we want to directly image an exoplanet. So one of the problems that this mission operations concept introduces is performing attitude control during the assembly. So when you're building something in orbit, you don't have a foundation on which to build. So you need to provide active stabilization in order to prevent tumbling. And conventional techniques for designing these controllers, you assume that you have measured all your mass properties at the start, you can measure them on the ground, and then you can design your controller accordingly. But for an on-orbit assembled spacecraft, you may be able to measure each individual structural element, but you won't be able to measure the whole thing. So the control system needs to be able to adapt to account for the changing mass properties during the assembly. So the goals of this study are to, one, develop the equations of motion for an on-orbit assembled spacecraft, specifically looking at how the mass properties change as you're assembling it. Second, we wanted to design an LQR controller to perform attitude control during the assembly, and I'll go into why we chose LQR as our approach later on. And then finally, we want to evaluate the LQR performance as the structure is being assembled. So this is the definition of the system that we're looking at. We have a spacecraft that's basically in two parts. We have the control spacecraft here, which has all the actuators and sensors on board. And then we have the structural element here, which has some sort of function aboard the spacecraft, but for us as the control designers, it's dead mass. It doesn't have any control actuation on board. So we need to provide the attitude control. So there's a more detailed derivation in the paper, but we developed the dynamics of this scenario using the Newton-Euler method. And specifically, we wanted to develop the equations of motion around the center of the control spacecraft. Normally, you would have the equations of motion around the center of mass of your spacecraft, since that decouples the translation and rotational dynamics. But because we're assuming that the center of mass may move during the assembly, we didn't want to consistently have to adjust recompute the moment arms between our control spacecraft and the center of mass. So we developed our equations just around a static point that won't move during the assembly. And you can see the important mass properties that show up in this equation. There's the total mass, so the mass of the control spacecraft plus the structural element, there's the location of the center of mass, and then there's the moment of inertia. So we can predict how the mass properties will change as we assemble the spacecraft using these equations. So the total mass is fairly straightforward. You just add the new mass of whatever structural element you're adding. You can figure out the new location of the center of mass based on the relative mass of what you're adding versus what's already there. And then for the moments of inertia, you can transform your moments of inertia from the body frame of the structural element itself to the body frame of the control spacecraft using the parallel axis theorem, and then directly add them. So because we want to use a linear control technique, we need to linearize our dynamics. So we assume that we're in a attitude regulation condition where we're operating close to a stable equilibrium point. So we have the velocity and angular velocity of the spacecraft are relatively close to zero. And then we can also assume that we can translate or transform our coordinate system to whatever our operating point is. That eliminates the rotation matrix between the body frame and the inertial frame. And what we're left with is a linear time invariant system that we can apply our control techniques like LQR to. So the reason why we chose linear quadratic regulator is that it's a model-based optimal control setup. And the powerful result of LQR is that if you have a linear dynamics and a quadratic cost function, you end up, the optimal control strategy is just a state feedback controller with a gain matrix that you can easily compute using this algebraic Riccati equation. And what we wanted to test in this study was, can we just, every time we add a new module to the spacecraft, can we just update our system model and recompute our gain matrix using the ARE to develop a new controller that performs adequately. So this is basically a block diagram showing what that would look like. So we tested our controller in a simulation. We decided to start simply with a one-dimensional beam structure. So we're assembling and we tested two different assembly sequences. So one assembly sequence is where we design our assembly sequence in a balanced method so that we add one structural module to one side and then one structural module to the other side so that the center mass doesn't move very much. And we just see what happens as we increase the mass in the moments of inertia. And then in the second condition, we consider what happens if we do allow the center mass to increase. So we just add all the modules onto one side, sort of like if you're familiar with the OSAM-1, OSAM 2 demonstration by Redwire, they're planning to basically 3D print a beam, so it's going to just extend out from the spacecraft. And then we tested this under two different disturbance conditions. So one of them was an angular disturbance where we set the initial yaw angle to 45 degrees and see if it can return to the commanded position at the origin. And then the second was we gave it an initial angular velocity of 0.25 radians per second and then saw if it could return to a stable condition. So this is the first of our simulations on the balanced assembly with the angular disturbance. So I'll explain what these plots mean. So over here on the left, this is our state. These are our states. So you have translational position, translational velocity, and then angular position and angular velocity. And then here you have our thrusters. So we have 4 pairs of thrusters, one on each side of the spacecraft. This is a planar maneuver. And then here we have an animation. I don't have the structural elements shown, but you can imagine structural elements coming out on each side of the spacecraft. And as you can see, simply by updating the gain matrix using the algebraic Riccati equation without tuning, without having to retune the gain matrix, or without having to retune the cost function, we were able to achieve stability as the structure grew. And so the main thing that changed was the time that it took to reach stability increased, and also the maximum thrust requested increased as well. And in velocity disturbance, we had a similar result where all the trajectories that the controller followed look roughly the same shape, but the maximum deviation from the stabilization point increased, because as the mass of your spacecraft is increasing and as the inertia is increasing, the total angular momentum when you give it that initial angular velocity is greater. So you need to provide more force in order to drive it back to, or more impulse, I should say, to drive it back to the equilibrium point. And then in the unbalanced case, this is where things start to get interesting, because we actually have some translational effects, because now the translational velocity and the rotational velocity are no longer decoupled. So you can see that as the spacecraft starts to turn itself, it starts to translate away from its equilibrium translational position. So our thrusters have to provide some force to compensate for that. And then this is the last simulation result I'll show. This is the same unbalanced assembly condition, but with a velocity disturbance. And you can see in the animation here, I've shown where the center of mass is. You can see it's way outside of the spacecraft, of the control spacecraft, but we're still able to return to an equilibrium condition. Right, you can see that the amount of force that the LQR controller is requesting is really starting to increase now. So obviously, you don't have unlimited thrust aboard the spacecraft, so that is an issue that we will need to resolve. So I'll go into the conclusions here. So one, we developed the linearized equations of motion, explicitly considering changes in mass properties. Number two, the LQR controller stabilized the nonlinear system near the operating point in all the cases that we studied. The next thing that we noticed was in the balanced assembly case, so if the center of mass is close to the center of your control spacecraft, LQR was always able to stable the nonlinear system, even if you moved far away from the equilibrium point. But once you started to move that center of mass out, that's where the linearized controller really started to struggle, because those nonlinear effects really start to dominate in those situations. And then finally, we noticed that the controller is requesting larger and larger control efforts as the mass and the moment of inertia are increasing. This could be compensated for by adjusting the Q and R matrices in your cost function. So you can deprioritize, or you can penalize thrust more, and that'll decrease the amount of thrust that the controller requests. So getting into the future work, we want to try some nonlinear control methods, like nonlinear model predictive control, to improve the translational control response and also explicitly consider thrust limits. We want to try adding additional control modules as well as structural modules, so that we can see if adding additional control authority helps improve the controller performance. And then lastly, we want to test this in hardware, so we're currently developing some air-bearing platforms at a lab that we can use to do that. Thank you. And this is a QR code that goes to our website. My contact information is there, and you can learn more about some of the ISAM projects that we're working on. Thank you.